Lagrange multipliers. In this section, you'll find it can be very similar to 14.7. In 14.7, we were looking for extreme values, and I'll get into more of the similarities in a moment. But this section ultimately is asking you to do the same thing. We're going to use Lagrange multipliers to find extreme values, maximums and minimums, in just a little bit different approach. Now, when you look for maximum and minimum values, we're essentially talking about optimization. Now, you dealt with optimization in Calculus 1, and in section 14.7, the methods we used in 14.7 were very similar to Calculus 1. Well, 14.8 is a much different approach, but it's going to lead you to the same sort of conclusions. Now, optimization problems do have boundaries or constraints, and these constraints generally do complicate optimization problems, since the optimal solution can occur at a boundary point as well as the interior of the function itself. So here we're going to investigate a very clever method for finding the optimal solution. It's called the method of Lagrange multipliers. In this section, we'll explain very briefly the geometric basis of this method. And then we'll start by trying to find extreme values subject to some sort of constraint. Now that phrase right there, subject to, right here, generally means you're dealing with Lagrange multipliers. You also can use the methods from 14.7 as well, but it generally means Lagrange multipliers. And we're going to look for extreme values that are restricted to some sort of level curve, in this case g equals k. And I'll show you a picture in a moment what that looks like. Essentially, what you're going to be trying to do is finding that specific point where your given function f subject to g, where f and g will intersect each other given these constraints. A really nice picture that's from the book kind of shows this geometrically how this works. As you can see here, we have all these different curves that we can use for f, right? But it's being constrained to the g curve here. And in this particular case, it looks like f is being maximized or minimized at this level curve, f equals 10, because it's only touching this one point here between the two curves. Now notice these two curves are just barely touching each other at that point. Well, because they're barely touching each other at that point, means that they have what's known as a common tangent line. And since they have a common tangent line, that means they also have respective normal lines at that same point that are identical. Now, what I mean by identical generally means parallel. And we all know that parallel lines are just simply scalar multiples of each other. And so you'll notice that here, this equation right here, the gradient of f, is going to equal to lambda times the gradient of g, where lambda is, it kind of throws some students off sometimes. They see that fancy new variable. It's nothing fancy. It's just simply a scalar. The book could have used any letter. It could have used C, K, whatever. Just decided to use lambda because that is common practice to use for Lagrange multipliers. It does indicate a Lagrange multiplier, which is a specific method. But it's just simply that. It's just a scalar, so do not get intimidated by this symbol here, lambda. Now, essentially, this can work not only for functions of two variables, but it actually can work for functions of three or more variables. Now, lucky for you, the most we'll do in this class is going to be f of x, y, z, so subject to functions of three variables. But the good news is that no matter if you are doing this method with a function of two variables or a function of three variables, it's the same process either way. And one more point to note out is that the point xyz is restricted to lie on the level surface S with the constraint of g equals to k. Now, this next slide here, it just basically maps out the method of Lagrange multipliers. And it's a lot of mathematical jargon that I don't really want to bore you with at this time. And it's basically something that I do want you to read on at your own leisure. But essentially, the Lagrange multipliers boils down to just 3 simple notes that I want to point out in the next slide. So again, read this at your own leisure. Don't worry about if you don't truly understand what this all says right now. But I do want to really point out part B down here. It says here, evaluate f at all points x, y, z that result from step A. The largest of these values is the maximum, the smallest is the minimum. This step B right here, okay, should be very familiar to you. It's exactly what you did in Calculus 1. It's exactly what we did in 14.7. Essentially, once you get all your potential extreme value points figured out, you simply plug them all back into your original function f, and the biggest will be the max and the smallest will be the min. So there's a huge similarity right there. So having said that, before we begin on some sort of example, let's take a look at some notes first. So first note, there's a lot of similarities in this section with regard to finding maxes and minimums. A lot of similarities. So that's the first note I want to point out. Second note. So again, keep that in mind. 14.7. If that's in the back of your mind, like almost half of the lesson for 14.8 is figured out already. Like you're basically already halfway there. If you can kind of keep that in the back of your mind, we're looking for maxes and mins. Second, all you're simply doing in this section is simply creating systems of equations. So each problem you're given in this section, you should eventually, and hopefully very quickly, set up some sort of system of equations. Now, we all should know this. A system of equations is essentially just algebra again. And if you understand your systems of equations from algebra, it's a lot of substitution, a lot of elimination, things like that. So really please make sure that you use your intuition when it comes to these things. Now, typically in this section, we're dealing with equations that have, or systems, excuse me, where you have either 3 equations, 3 unknowns, or 4 equations, 4 unknowns, and sometimes 5 equations and 5 unknowns. And that's pretty much as high as we'll get, but keep that in the back of your mind as we're kind of dealing with these. And lucky for you, I don't go past that, but Lagrange multipliers does go beyond 5 equations, 5 unknowns. It goes as much as you want. But lucky for you, we're sticking to, at most, 5 equations, 5 unknowns. And finally, third, the note that I want to point out is this. Be sure to constantly use your intuition and your savvy in algebra. Not all systems have to be solved the same way. Just because you solved the system one way in a previous problem does not mean you'll solve it the same way in another problem. So please keep that in mind as we progress through this section. Okay. So for our first example, we're going to go ahead and look for the maximum and minimum value, but we're going to use Lagrange multipliers. Now again, you're welcome to use the methods from 14.7 to solve for this. And I would actually recommend that as you're getting ready for your next exam, go ahead and do all these problems using both the methods from 14.7 and the method here, Lagrange multipliers. And make sure you really have both those methods down well. Don't prefer one over the other. Just try to understand both. So for this example here, we have everything we need. We have our function, and this here is going to be our constraint, or our level curve, 4x squared plus y squared equals 8. Let us begin. So f of xy equals xy, and the constraint is going to be 4x squared plus y squared. So what's going to happen here is we're going to go ahead and let f of xy and g of xy, we're going to let g of xy here be 4x squared plus y squared. And therefore, I think we all could agree, we should be pretty good at this by now, that finding the gradient should be pretty easy. I think we all could agree that our gradient of f is yx, and our gradient of g in this case is 8x 2y. And if you're wondering where did this 8 go, this constant, again, it doesn't really matter because we'll be taking the gradient of it. It'll come back later, trust me. This will definitely, this number 8 up here will come back later. But moving forward up till this point, we are not going to use this constant 8. And so what we're going to do is we're going to go ahead and take this equation. This is really the equation that I want to really point out. This gradient of f equals to lambda times gradient of g. In fact, let's go back real quick and take a look at that. This equation right here is really, in fact, let's kind of point out this guy. This is the equation you really want to focus on. Okay, it's the gradient of f times equals the lambda times the gradient of g. And basically, what all you're doing is essentially replacing gradient of f with yx, the gradient of g with 8x 2y over here, and that becomes this. And it's just a simple matter of me substituting out gradient of f with the yx and the gradient of g with the 8x 2y. So this here, is being plugged in over here. Yes. And this here is going to be replacing this guy. Okay. So end up with this equation here. And think back to chapter 12, where the first component of this vector is equivalent to the first component of the other vector on the other side. So if I take lambda and I simply distribute it into the vector here, okay, then I simply get y equals to 8 lambda x. So again, lambda is being multiplied into here, and then x equals to 2 lambda y. So again, it's just simply the first component equals to the first component, and then here's the second component equals to the second component. And the whole point is that, again, I said earlier, Lagrange multipliers is all about creating a system of equations. So now a system of equations here, I already have my first equation. Here's my first equation. Here's my second equation. So what's my third equation? Well, my third equation is going to be the constraint. So along with my constraint, what's my constraint? Well, that's this guy up here. This is our constraint. Along with our constraint, our system of equations becomes this right here. Okay? There's my first equation from before. There's my second equation from before. And here's the given constraint I was given at the beginning of the problem. Now you'll notice I do this a lot. Once I have my system of equations set up, I go ahead and label my equations 1, 2, 3, or 1, 2, 3, 4, 5, or whatever I need to do. It's just going to help the notes flow a little bit better. And I recommend you do the same too. That way you can keep more, keep things more organized and be more precise in your work. So I recommend you number your equations also. So here are some thoughts. Now now look. Here's the thing. Before I even begin, just remember Lagrangian multipliers are you're gonna have to have some patience with them. In fact, the thoughts I have on each system that I present in this class for this section are going to be like a lot of intuition, a lot of playing around with values. So be willing to play around with values until you get something that sticks. The nice thing is that you can kind of plug in whatever value you want, and if the value works for the first equation and the second equation and the third equation, then you know you have a point for a possible extreme value. But the nice thing is whatever value you plug in, chances are if it doesn't work, it's going to contradict one of the other equations. So let's go ahead and take a look. Now, one great number to always work with is the number 0. So let's go ahead and look at the number 0 here. If I let x equal 0 and y equals 0 at the same time, then obviously it's going to work for the first equation. Obviously it's going to satisfy the second equation. Everything just kind of cancels out. You get 0 equals 0. However, what's the problem with x equal to 0 and y equal to 0 when it comes to the third equation? You'll notice what? According to the third equation, it gets contradicted. So now you might be wondering what was the point of checking that. Well, it's always a good idea to check, x equals 0, y equals 0. Those are very easy values to check, and you can quickly see that it's going to contradict something, or you might get lucky and then 0, 0 might be one of your points. But because it contradicts the third equation, we actually need to search other possibilities. And so because we're going to search other possibilities, let's take a few other options. So here's another possible method. Now, there's so many possible methods, okay? Notice that equation 1 and 2 both have lambda in it. So one possible method that you'll find helpful whenever you're doing problems like this is just going ahead and solving for lambda. So if you go ahead and just solve for lambda in equations 1 and 2, that gives us the following. Okay, so for equation 1, if I solve for lambda, I get y over 8x. In equation 2, if I solve for lambda, I get x over 2y. And the nice thing about solving for lambda, a nice thing about this approach is that notice that they both equal to lambda. And because they both equal to lambda, I can actually just set them equal to each other. And because I can set them equal to each other, I go ahead and just cross multiply here, right? So we cross multiply. This up here, right? And I end up getting 2y squared equals 8x squared. And then you just basically start solving, right? Well, notice here I get y squared equals 4x squared, right? Now, the temptation here would be to square root both sides, and you're welcome to do that. But what's nice here is, again, using your intuition. If you just take this relationship here, notice that x squared equals to 4x squared, right? Well, what if I just, instead of taking the square root on both sides, I just go ahead and substitute that into equation 3. Notice, look at equation 3 here. Equation 3 has both 4x squared and y squared. So what if I just go ahead and substitute y squared with its own 4x squared? Substituting this into equation 3 essentially gives me 4x squared plus 4x squared equals 8. And I guess this should have been, I should have circled the second term instead, but I think you get the idea. So again, substituting this relationship into equation 3 causes us to have 4x squared plus 4x squared equals 8. And then we solve for x, we end up getting plus or minus 1, of course. And then guess what I do with these values? Well, what I do with these values is substitute those back into the previous relationship here. Now notice I just used the word substitution or sub twice. Well, wasn't that a very popular word in 14.7 as well? And this is where you're starting to see some of the similarities between 14.7 and 14.8. All I'm simply going to do now is substitute it back into this equation. We end up getting, if I plug a plus or minus y into here, we end up getting this here. Y squared equals 4. Square root both sides, we get plus or minus 2. And we're not fully done, but believe it or not, the hard part is done. The hard part is done. We're almost done, actually. The point is, I got two options here. I got not only do I have x equals to plus or minus 1, but also y equals to plus or minus 2. And the point is that we need to check all possible extreme values. And all the possible extreme values are plus or minus 1 and plus or minus 2. So if you guys already kind of can see, that means there are 4 possibilities here. But guess what I do with these 4 possibilities? I simply evaluate f at every single one of these points, and then we'll be done. So I'm going to go ahead and take these points here. There's 4 possibilities, and we're going to plug it in to f itself and find out what's our min and what's our max. So remember, guys, I'm going to take these values here, and we're going to plug them into the original function given to us. Oops, that's the next problem. And you plug these into here, and that'll give you your min and your max. And now this one's a fairly simple example. The next one is going to require more thought and more intuition. But that's essentially the idea. And let's go ahead and just kind of summarize real quick. Okay, so the first step is to find the gradients. Okay, plug it into this all-important formula right here. I mean, this is Lagrange multipliers right here. This is the main formula right here. Okay, plug it into here, and then this equation will generally give us two or sometimes 3 other equations. And then these 2 equations get thrown into a system of equations, so along with the constraint. And then you just start using algebra, start plugging in values, start playing with values, doing whatever it takes to solve this system. Once you find those possible points, you plug them into the function f and get your maxes and your mins. So let's go and try another example. This one is a little bit more difficult because not only do I have x and y, I also have z. So this is a function of 3 variables. Here is my function e to the xyz, and here is our constraint. Now remember, when we initially use our constraint, this 24 won't matter for a little bit, but then this 24 comes back when we set up our system of equations. So in this particular case, guys, there's my function f, and my function g, the constraint is in this case 2x squared plus y squared plus z squared. Using again that all-important equation here, we end up with this, which I think we all can agree with. I think we all can agree that the partial derivative with respect to x of f here is going to be e to the xyz times the chain rule. The derivative with respect to x of xyz is just simply yz. So again, this should be pretty simple for us because this was from our section on partial derivatives. And I believe we all can see that this is the partial derivative with respect to y, this is the partial derivative with respect to z, and then equals to lambda. And again, remember, we're going to take this lambda and we're going to distribute it to all 3 terms here. Okay. And again, now these are the partial derivatives for our constraint here. So obviously 4x is definitely the partial derivative with respect to x of this guy here. 2y and 2z follow suit. Once again, along with the constraint, we now have our system of equations. Now in this particular case, our system of equations doesn't just have 3 variables, it now has 4 because we have x, y, and z, but then we also have lambda. So if you ever have 4 unknowns, you need 4 equations, and that's exactly what we're going to have in our new system here. So my new system is going to be, our first equation is going to be, again, the first component is equal to the first component along with that lambda. Okay, see again, the lambda gets distributed. So it's our first component equals to the first component. Hopefully that makes sense. So as we can probably understand, the second equation is going to be the second component equals to the second component. and the third component equals to the third component. And finally, our fourth equation is the constraint itself, which is that constraint we were given in the first place. And now it is up to us to figure out how to solve this monstrous system of equations. Now please, again, do not be intimidated. This does take time, it does take practice, and you will get at least one of these. I should say you only will get one of these on your next exam. You will definitely get one problem like this one on your next exam, so you have to actually do practice. Now again, you're welcome to use the methods from 14.7 to also check your work. But remember, there's only so much time when we take these exams. Now what I recommend we do for this one is, why don't we just go ahead and play with some numbers first. Let's just play with some values. And, you know, again, what is the easiest value of all? What's the easiest value to start with? And you guessed it, it's the value of 0. So let's talk about that for a second. Let's ask yourself, what if any of these, x, y, z, or lambda, what if any of these were equal to 0? Just any one. What would that imply? Well, let's go ahead and take a look at this system as I scroll up here. If I plug in a 0 for x, let's say. Let's plug in a 0 for x. So if I plug in a 0 for x here, right, then that means this goes to 0, which means this guy equals to 0. Well, the only way that the algebraic expression here on the left would equal to 0 is because if x equals 0, that's not going to make it go to 0, but if one of these other two variables equals to 0. So if x equals to 0, then that means that at least x, y or z must be 0 also. So, okay, again, I'll say it one more time. If x equals to 0, then that means at least y or z also equals 0. So if any one of these variables, x, y, z, or lambda, equal to 0, then that implies that at least two zeros from x, y, and z are also 0. So why don't we go ahead and take it to the next extreme? Okay, could all three be 0? Could all three? Could x equal 0, y equal 0, and z equal 0? Well, the answer is no. Why not? You always have to keep an eye on your constraint. So x can't equal 0. X can equal 0, y can equal 0, but z could not, or any other combination. So not all three can be 0. However, we did kind of prove that at least two zeros are going to come from either the x, y, or the z. So at least two of these would be 0. That's true. And by the way, this is just one possibility. This is just one possibility on how to initially solve this problem here. Okay, so, well, since not all three could be 0, what that tells us is the following. What that tells us is that one possibility is that exactly 2 of x, y, or z equals 0. Exactly 2. So either x and y are 0, but z is a non-zero. Y and z are 0, x is a non-zero. So on and so forth. So how do we go about doing this? Well, what you do is you basically come up with your first set of possibilities. Since we know that one possibility is that exactly 2 of x, y, and z equal to 0, go ahead and start experimenting. So what we do is we go ahead and take equation 4, and let's just go ahead and pretend that y and z are both 0. Y is 0, z is 0. Well, if that's the case, if y and z are 0, this is 0, this is 0, we get 2x squared equals 24. And then solving for x would end up giving us plus or minus 2 radical 3. So that's one possibility. And this is one possibility for your extreme values. Or what if x and z are 0? Well, if I plug in x is 0 and z is 0, then y is going to be plus or minus 2 radical 6. And finally, what if I take the possibility of x and y being equal to 0, then z will be plus or minus 2 radical 6. Again, these are all being plugged into equation 4. And notice we have here 6 possible extrema. Now, once you have your possible extrema, you actually are supposed to plug it back into F. And if we plug any one of those back into F, we see we actually end up with a value of 1. So yeah, if you don't believe me, go ahead, plug in any one of these values back into your original function F. Okay, that's this guy here. Plug any one of those into here, you'll just get 1 every time. Okay. Now, here's the thing. You might think we're done, but we're not. This was just one possibility. This was just us playing with the number 0. Well, what if xy, what if none of xy nor z nor lambda are 0? What if we didn't have any zeros at all? Could that be a possibility? Again, this is just us playing with numbers. And before you get concerned, just understand you'll get better and better at this. And I will be requiring you guys to use Lagrange multipliers for one of your test problems. So make sure you know this method. So here's another way to solve. So what if we try another method? Here we go. So let's try this method here. Let's try just rearranging 1, 2, and 3. And what do I mean by that? Well, if I took equation 1 and solved for e to the xyz, I get 4 lambda x over yz, which I don't think that's difficult for anyone to see. Now let's go ahead and do the same thing for equation 2. Simply by solving for equation 2, solving for e to the xyz, we get 2 lambda y over xz. And again, similarly for equation 3, solving for e to the xyz equals 2 lambda z over xy. And if you are wondering, how would I know to do that? Well, it comes from experience, practicing a lot, and just noticing commonality. So I noticed that they all had an e to the xyz in common. So I'm going to go ahead and solve for that. Now, also, we could follow this formula or this problem the same way I did in the last example, where at this point we solve for lambda, which is fine also. This is just another way to do it. And again, you're going to be free to do whatever you wish to do and whatever it takes to solve this problem. Now, obviously, since they all equal to e to the xyz, you can go ahead and set them all equal to each other. And as we set them all equal to each other, you'll notice that they all have a lambda in the numerator. So that means, obviously, lambda can be easily removed, which means it's one less thing to worry about. And what I want to say is that what's happening here, it's creating relationships here, right? So if you notice the first set of expressions here, if I go ahead and cross multiply these two right here, I'll get back to this guy in a second, but if I cross multiply those two guys, I end up getting this relationship here. I get a new equation. In fact, I'm going to even label it equation 5. So if I, again, cross multiply these guys, I think we can agree with that. And then if I do the same thing, if I cross multiply these other two guys, I end up with the second equation. I'll call it equation number 6. And again, I just basically got these two relationships, equation 5 and equation 6, based off of just cross multiplying. And you can cross multiply these however you want, but you'll notice that we get these relationships here. And once you've established relationships like this, and now these are really nice, this is a really fortunate situation, because notice that they both have a y squared involved. And again, the temptation is going to be to solve for y or solve for x and get plus or minus. you are welcome to do that, and it's not wrong. But sometimes things are a little bit easier if you keep these squared for now. And at this point, go ahead and just sub these back into the constraint. So again, there's that word again, substitution, substitution, constantly, right? So I'll be taking these two relationships and subbing them back into equation 4. Well, here's equation 4 again to remind you. And if I replace anywhere, you can replace it however you wish, but me personally, I'm going to replace 2x squared with y squared and replace z squared with y squared, giving me nothing but y squares, which obviously is 3y squared equals 24, which solves to become 2 rad, plus or minus 2 rad 2. And then guess what word's coming up again? Substitute once again. This time I'm going to substitute these values back into the relationships found in 5 and 6. And by doing that, we obviously get x is plus or minus 2, and z is plus or minus 2 rad 2. So if you plug these back into 5 and 6, you'll get these values here. So let's just kind of summarize here before I continue. So far we have these 6 possibilities up here of extrema, but now we got all these possibilities. We have plus or minus 2 rad 2, plus or minus 2, plus or minus 2 rad 2, which gives us a ton more possibilities. So yet more possibilities of extreme values. Now, this is a pretty in-depth problem. And at this point, you're thinking, man, I don't really like these Lagrange multipliers. But I'm telling you guys, it's a very beneficial method. It has its pros and cons, of course. But notice here that we have all the values that we need to plug into f and find out what is our min, what's our max. And yes, unfortunately, we do have to consider plugging in all the combinations. Now, there's a yes and no to that, though. If you notice patterns, and if you see that some points are going to give you the same values, you don't necessarily have to plug them on in. I certainly don't need to see you plug in every single value if you're noticing patterns. But the point is that if you notice, no matter what combination you plug into f, you'll notice, for example, in this one, so you might think, oh man, this is why I don't like Lagrange multipliers, because I have to plug in all these different possibilities. Well, in this particular case, we actually got kind of lucky. In this particular case, if you actually notice, no matter what combination I plug into my original function, which is e to the xyz, there's actually only 2 possible values that we can get. And those 2 possible values that we get are e to the 16 and e to the negative 16. So therefore, our max value is e to the 16, our min value is e to the negative 16, and we're basically done. But also keep in mind, guys, that earlier we found that one of our potential extreme values was e to the 0 power from earlier. But I think we all can see that e to the 0 power is between e to the negative 16 and e to the positive 16. So we can just disregard it. So this here is our answer. So yes, I know, quite a bit of work just for one problem. But one thing I really want to point out about this method, it is consistent. It is so consistent. And I, for one, think that 14.7 is a very consistent method as well. And it's always nice to have some consistency. Let's go on to another example. Use Lagrange multipliers to find the maximum volume of a rectangular box that's inscribed in a sphere of radius r. You definitely recognize this problem because we did the same problem in 14.7. So it's the exact same problem, so we already know the answer. In fact, you're welcome to go back and look at the answer from the previous section. But what I want to point out with this problem is that with this problem, we're going to do the same exact, find the same exact answer using Lagrange multipliers. Okay, so it's the same problem, now only with the Lagrange multipliers. And as I do this problem, please take careful note of the similarities between what I do here and what I did in 14.7. Now, let's go ahead and just let our dimensions be the same as before. So our aim is to basically maximize the volume, length times width times height. And from the dimensions from the previous section, our dimensions were 2x, 2y, 2z. Now, if you recall, we ended up replacing z with that square root of that really ugly expression. So we actually ended up with a really ugly volume expression. So one advantage that Lagrange multipliers has is that you actually can keep your expression as just the simple, very nice and pretty 8xyz. It actually can stay exactly like that. Now, we know that this box is subject to the sphere. That's what it's subject to, the sphere of radius r. This is the thing we're going to be trying to maximize, the volume here, 8xyz. So our problem becomes, we're going to try to maximize this function, 8xyz, subject to the constraint of the sphere. And now, from this point forward, I can almost stop and say, okay, go ahead and do Lagrange multipliers. You can figure it out from here. But again, I'll show the steps. It's fine. But my point is, it's going to be the same exact steps. It's very methodical, very consistent. So once again, we're going to use the all-important equation here for Lagrange multipliers. We're going to take the gradient with this, the gradient of f here, and the gradient of g in this case is going to be the x squared, y squared, z squared. R is a constant, so we ignore it for the time being. And that gives us this. And hopefully that makes sense to everyone. I went ahead and took the liberty of distributing the lambda into this vector. Which is going to give us a system of equations here. So my systems of equations, my first equation is obviously 8yz equals 2 lambda x. Hopefully that makes sense. Again, first component equals first component. Second equation is second component equals second component. Third equation is third component equals third component. Okay? And of course, our fourth equation is the constraint itself, the sphere of radius r. Now again, you are welcome to solve this system of equations any way you see fit. Whatever gets you through the problem, please use those methods that you know from back in the day, your algebra methods, your algebra skills. In fact, many times students do things I wouldn't even have expected and do things a lot more even efficiently than I do. So please feel free to do whatever method you see fit. Now, the method I think is good for this one is a suggestion. We've done this before. We'll do it again. Let's go ahead and try and look at the commonalities here. If you'll notice that all three equations all have a lambda in common, and the lambda is in the same exact spot. So in this case, I'm going to go ahead and solve for lambda, giving me this. And actually, at this point, it becomes exactly like the last problem when I went ahead and just cross-multiplied the first two expressions, and then I cross-multiplied the second two expressions. So by cross-multiplying a few of these, we end up with yet another equations 5 and 6. Found a very similar way to the last example. And this one ends up giving me x equals y and y equals z. Well, by law of transitivity, if x equals y and y equals z, that means x equals z. Therefore, x equals y equals z. Take this relationship, and now it just kind of falls like dominoes. We substitute it into 4. So x squared, y squared, z squared becomes x squared, x squared, x squared. Solving for x, we end up getting r over rad 3, which we saw in the last section, which means all three equal the same thing. Therefore, the largest box would be f evaluated at that point, which equals the same exact answer we got in 14.7. Let's try one more before we move on to a little bit more complicated Lagrange multipliers. Yes, it gets a bit more complicated, but again, the same process. Here, we're going to go ahead and try to minimize the surface area of a box that has volume of 1,000 centimeters cubed. So here, if I let my surface area have, the box is x and y and z are the dimensions, then obviously my surface area is going to be 2xy to represent the floor and the ceiling, 2xz to represent the right wall and the left wall, and 2yz to represent the, that's the left wall and the right wall, and then 2xe is the front wall and the back wall. I think this is familiar to most of us who've ever taken a geometry class. And again, we all know volume is length times width times height. So according to these dimensions, that would be x, y, z. Now keep in mind that this particular problem, the box is subject to the volume in this case. In the last problem, we were searching for the volume. In this problem, the volume is the constraint. So I'm going to go ahead and let that x, y, z be my constraint of g. If that's the case, our problem becomes f is the surface area I'm trying to minimize, subject to x, y, z equals to 1,000. And again, honestly, I could just say here, hey, go ahead and take the reins. You should basically follow the same methods that we did in the last three examples, I should say, to find the values where you get a minimal surface area. But again, I'll go ahead and show how to do that. Once again, we take the all-important Lagrangian equation here. That gives us this equation here. This here is the partial with respect to x. This here is the partial with respect to y. This here is the partial with respect to z. Again, we're going to take lambda and we're going to distribute it, which will lead to our system of equations. Here's my first three equations, and of course, you could probably guess what's going to be my fourth equation, which is the volume of the box itself. Once again, this is coincidental. It doesn't always happen. But again, I think this is also another candidate where you should solve for lambda. Solving for lambda, notice that in this case, once again, we get x equals y equals z. Again, just a coincidence. And by subbing the fact that x equals y equals z into our constraint, it gives us x times x times x, which is x cubed. Solving for x, we get 10. So x is 10, y is 10, z is also 10. And before I move on to the next example, you might have noticed that in all these examples I've done so far, we have yet to find a value for lambda. And the good news about that is it's just a scalar multiple to create parallel vectors. That's how the Lagrange Multipliers method works. So just remember that we don't really need to know what the value of lambda is. So don't ever be concerned about that. Now, occasionally there are problems where you could, I suppose, plug in values for lambda if it helps. But largely you don't even need to find an explicit value for lambda. All right, here's where we really ramp up the complexity. Now, I shouldn't even say that because I might intimidate you or scare you from this next portion, but it's really not that bad. Here we're looking for where we can have two constraints, not just one, which also, yes, it's more difficult to solve, but it does lend itself well to much more complicated situations, much more complicated optimization problems that can be solved now with two constraints. And it's basically, here's a pretty complicated picture, but it's going to maximize, the whole point is we're trying to maximize some function, f of x, y, z, being subject to two constraints. And notice that you could have three or more variables here, again, just like having only one constraint. And geometrically, we are looking for the extreme values of f when xyz is restricted to lie on some specific curve of intersection C. And it's kind of hard to see here, but it's that little curve right here that's being intersected between those two surfaces. So instead of just having lambda, we're going to have not just one Lagrange multiplier, we're going to have two. And it does lead us to a slightly more complicated equation. But what I want to really point out here is that this equation at the bottom here is very similar, or it's similar in nature to this equation here that we've been using this whole time. So I'll say it again as I scroll this up here. This equation down here is same in nature as the equation we've been using this whole time. So we're going to be setting up some sort of situation where we have a vector equals to a scalar multiple of another vector. But, well, I should say a linear combination of two vectors. And basically proceed from there, and still we'll be looking for a system of equations, is the idea. So really, the concept is not changing at all. It's only adding a little bit more of a layer of complexity is all. So why don't we just go ahead and dive right into an example. So here, again, I want to reiterate, it's the same concept, just more stuff, more equations. So yes, you're going to get a more complicated system of equations generally, and you're going to have to use your algebraic savvy to get through all that. But it's the same concept. But here, we're going to let f of x, y, z equals z, and it's going to be subject to the following constraints. The two constraints are going to be g is going to be x squared plus y squared minus z squared. And the reason that is because you need to subtract z squared over here to the other side, set it equal to some sort of constant, and that becomes our g. So that's why this last term here is negative. And this one is already equal to 24, this constant. So again, for temporarily, we're going to ignore this constant, and we're going to let h be our other constraint, which is x plus y plus z. Okay, so this is our Lagrange equation here. Okay, and before I show you the answer to that, let me just kind of dissect it. The gradient of f is super easy, right? The gradient, the derivative with respect to x, then the derivative with respect to y, derivative with respect to z. That's pretty simple. But then the same thing happens over here. We need to find the gradient of g and the gradient of h. And we end up getting, this is the gradient of f right here. Okay. This is the gradient of g, and this here is the gradient of h. And notice I have lambda in front of this one, and this is mu in front of this one. We're going to go ahead and distribute those in, distribute that mu in as well. And on top of that, I'm going to go ahead and take the liberty of, and sorry, this should actually be a vector bracket, sorry about that. I'm going to take the liberty of not only distributing the lambda and the mu, but I'm also going ahead and add up the first component with the first component. So as you can see here, I have 2 lambda x plus mu. And then I'm going to add the second component with the second component. That will give me 2 lambda y plus mu. And then finally, the third component plus the third component gives me 2 lambda z plus mu. And right away, we're going to get our system of equations, where we set the first component on the left equal to the first component on the right, the second component on the left equal to the second component on the right, and the third component on the left equal to the third component on the right. And like I said earlier in this lesson, I said we do get up to 5 equations with 5 unknowns in this class. And here she is. My first 3 equations are coming from the Lagrange multiplier formula. Okay, that's this guy right here. And then we have 2 more equations to go, and the 2 more equations are going to be what we got in the very beginning, which are the constraints. And again, if you're wondering where I got those from, was from the original problem right here. Okay? 5 equations, 5 unknowns. Now again, before you truly dive into a problem like this, what I highly recommend you do is you, again, just play with numbers. Like, play around, see what you got, see what you can do. Just have fun with it if you think this is fun. So for example, if I first take a look at the first two equations, take a look at equation 1 and equation 2. One suggestion I have for you is to go ahead and solve for mu for the first two equations. So notice from the first two equations, if I solve for mu in the first equation, I get this, mu equals negative 2 lambda x, and then, which also, mu equals here to negative 2 lambda y. And the only way this is possible is if either lambda is 0 or x equals y. That's the only way that's possible. So if I just get, again, this is me playing around, just being flexible, trying not to, let myself get flustered too easily. And if I let either lambda equal 0 or x equal y, then let's go ahead and kind of test those. Okay, so I have two different cases here. So this is going to be case 1, and this is case 2. So let's go ahead and test out both of these cases. Let's first test out the case of what if lambda equaled 0. Well, if that's true, if lambda equals 0, let's go and plug in a 0 up here. So if lambda equals 0, then mu must equal 0. I think we all can agree with that, right? But the problem with that, though, is that if mu equals to 0, that's going to contradict the third equation. Because if lambda equals 0 and mu also equals 0, well, 0 plus 0 is not equal to 1. That's going to contradict it. So what's nice about that, because if lambda equals 0 is a contradiction, we can go ahead and just, cross that possibility out and move on to the other possibility, which is the possibility of x equaling to y. So in this case, x is possibly equal to y. So what do? We take that and we substitute it into equation 5. Now, you might wonder, well, how'd you go from equation 1, 2, and 3 and then jump over equation 4 and then go into equation 5? Well, it's just by my own choice. You can actually go ahead and you're welcome to plug that into equation 4, but you'll notice that if you plug this this fact into equation 4, to me it becomes a more difficult algebraic situation. And we want to try to make the most simple algebraic scenarios possible. So I think that plugging this into equation 5 makes things much more simple. So if we go ahead and take equation 5, here it is again, replace x with y, or excuse me, y with x. Now obviously we have no replacement for z yet. But then notice, if I go ahead and solve for z, I now have a relationship between x and z, yes? And then guess what I do with that relationship there? You could probably already guess what word I'm going to use. It's all over the place, right? We're going to substitute that into equation 4 now. And don't forget, not only am I going to replace z with 24 minus 2x, again, please don't forget, this is all based off the case we're using that x equals y. So we're gonna substitute this relationship and this relationship into equation 4. So once again, here's equation 4. Replace these values that we're talking about into equation 4. So x squared stays x squared, y squared becomes x squared, z squared becomes 24 minus 2x quantity squared. Now, using algebra, I should not have to tell you guys how to solve this, but using algebra coming from here to here, we end up getting 24 plus or minus 12 radical 2. I use the quadratic formula to get that. And again, since x equals y, not only does x equal 24 plus or minus 12 rad 2, y also equals to 24 plus or minus 12 rad 2. Once again, we substitute this value into z. So you plug those into z, and we end up getting a couple different possibilities. So if you plug 24 plus 12 rad 2 into here, we end up getting negative 24 minus 24 rad 2. If you plug in 24 minus 12 rad 2 into this relationship, we end up getting negative 24 plus 24 rad 2. The nice thing about this problem is that even though it's quite in depth and there's quite a lot of moving parts. The nice thing about this problem is that there are only 2 possible points this time, so that's nice. Whereas the last problem had 12. So silver lining, I guess. So then again, you go ahead and you take these fairly complicated numbers, you plug them back into the original function that was given. Now this one's actually quite simple because obviously since f only equals to z, you only have to look at the z value here. And I went ahead and took the liberty of just plugging it into my calculator. So obviously our maximum is at this point with the maximum of 9.94, and our minimum is at this point with a minimum of negative 57.94. Okay, let's take a look at one more example. Now, this last example, it's nice because we only have one constraint. So we're back to only using lambda, not lambda and mu, so that's nice. There's only one constraint here. And also, this problem is very similar to what we did in 14.7, where we first looked at the interior of some region, and then we had to also look at the border. So we actually have a lot of experience with this. In fact, this problem also, you can use the methods from 14.7 to do this problem. And I would ask you to try it. And in fact, moving forward, any homework problem you do where they ask you to find extreme values, I would challenge you just to get better at these, to do both methods from 14.7 and 14.8 to really solidify your ideas of how to do both these methods. And if you have a little bit of extra time on an exam or a quiz, it'd be a good idea, like, if you had extra time to finish up a problem, you can always try the other method to confirm your results. Now here, what I'm going to basically do for you, what I'm going to do for you guys is just kind of set it up. But just remember, this thing actually starts off just like the last section. For this problem, we must first check for critical points. Again, remember CP means critical point. And just recall back, how do we actually check for critical points? Well, what we do is we go ahead and find the partial derivatives. If you guys recall, to do this, what we're going to do is we're going to find the partials with respect. Excuse me, sorry about that. We're going to find the partials with respect to x and with respect to y, and solve for them by setting them equal to 0 and solving them simultaneously. And again, I'm saying recall here, so I'm hoping that most of us know exactly how to do that and what I'm talking about here. We've done this several times already. So, okay, pretty simple. Here's my function up here. If I take the partial with respect to x, I get 2x plus 4. The partial with respect to y, I get 2y minus 4. Set those both equal to 0. We get a very simple, this is a very simple critical point of negative 2, 2. Okay, so there's one point. And again, any point you find, you're going to ultimately plug into the original function to find out if it's a max or a min. Now, before I continue, though, make sure that this point is within your region. Now, since we're talking about a disk that's centered at the origin of radius 3, then obviously negative 2, 2 is certainly within the region. Now you go ahead and take this point here and go ahead and plug it into the function itself. We end up getting negative 8. And we're going to go ahead and keep this in mind for later. Now that I have the interior, this is inside the disk taken care of, which has nothing to do with Lagrange multipliers. Lagrange multipliers are when we check the border. So our problem becomes the following. It's the same function, x squared plus y squared plus 4x minus 4y, but now we are subject to not the interior of this disk, but the border of the disk. Now, because we have done several examples already, and we've done several examples that are much more interesting and much more complicated than this one, I'm going to leave it up to you to go ahead and work this one out, but I'm going to go ahead and give you the answers. Now, before I actually show you the answer and leave it there, you get multiple points that are possible extreme values when you do the Lagrange multipliers. But you'll find out that the max occurs at this point, 3 over rad 2, comma, negative 3 over rad 2. So I would ask you to do Lagrange multipliers to figure out how I got to this point and end up getting this value right here. And then your minimum, now there is going to be a Lagrange multiplier point that's going to be less than this, but you'll find out that the actual minimum is actually going to be on the interior of that disk. And that doesn't always happen. Sometimes you'll do a problem like this, and both the max and the min both occur on the border using Lagrange multipliers. In this case, though, we had a maximum that occurred on the border and a minimum that occurred on the interior. And finally, before I conclude this lesson, please try the above problem and try every single problem you've seen in this section using methods from 14.7 and vice versa. As you're finishing up your homework for 14.7, you should also keep in mind to try to do Lagrange multipliers on those very same problems.